Welcome to Radar System course. Today we will learn a delay line canceller, and this method of a delay line canceller is useful for displaying the information on the display devices. So now sometimes what happens when we have a target, okay, when we are identifying any target, in that case the target is supposed to be a moving. So then it is difficult to identify that particular target. Okay. So this one is for the moving target, that is about the velocity of a moving target, and we are supposed to send a radar signal there. When we are identifying a moving target, in that case the signal we are transmitting, that is about your transmitting signal ft, and we are supposed to receive we are getting the echo signal from the same target. From that we can find out the range, but again we need to know about what will be the speed of that particular target. So that echo we are receiving from the target, if that particular echo we are receiving the frequency of that particular echo signal, as well as the signal we are receiving from the stationary object, that is called as a flutter, if they have the same frequency, in that case we are not able to identify that there will be the moving target. So that's why what we can say that at that particular response, the delay line canceller response will be a zero at that given particular frequency. This echo, that will be the FD, and we are getting the at the same particular frequency signal. So that's why from the clutter stationary object. So to remove that stationary object, the same FD will be removed. Okay. So means we are getting the echo from what? Echo from a stationary object, and we are getting the echo from what? A radar. When that both the signal frequencies are same, okay, so that's why what we can say that so the response of this particular delay line canceller will be zero at a given particular frequency. So that is nothing but a blind speed. Okay, that is nothing but a blind speed, means the target is there and the target is moving, but we are getting the echo with the same frequency from the clutter, that is about a clutter echo or clutter signal we are getting with the same frequency that we have observed from the target. In that case, the response of this particular delay line canceller will be zero. If the response will be zero, so on a display we are not able to see any target. Okay, we are not able to show you any target. That is about the issue, and that particular frequency response where we are getting the zero target, or we can say that your echo from the stationary signal as well as the echo from the radar, that FD, what we can say that echo from the radar is nothing but the FD, and this one, if it is the same, okay, so then what happen? So we will get the zero response across this delay line cache. That is nothing but a blind speed for the delay line cache. So now what happened here? What happened here in a delay line canceller? At a receiver, we are getting a bipolar video. Now that bipolar video is to be given to the delay line. Okay, so if you see that in delay line cancellers, we have a receiver there. Okay, this one is about our receiver, and from the receiver we are getting the output, and that output is to be given to the delay line. This one is about a output from the delay line. So output from the delay line, that is to be given to the a subtractor. That is to be given to the subtractor, and subtractor has a two input. One is directly the input from the relay line, and one is from directly from the receiver. And so here we have a bipolar video. We have a bipolar video. Okay, this one is about a bipolar video. Now that output, if we provide the output to the full subtractor, okay, or we need to convert into A to D and all, so then at the end we'll get that video, that is output is nothing but what, to the unipolar video. That output, full subtractor output, is to be given to the display device, okay, or we can say that to the indicator. And here we are getting the unipolar video. We are getting the, here we are getting the unipolar video. So after subtractor, we have a full subtractor there, and that full subtractor will remove the whatever the component. So generally, what here, this delay line canceller, it acts as just like filter. It acts as a filter. It just eliminate the component from the fixed target, because clutter we are getting, that clutter is about from the fixed target. So that's why it eliminates only the component which has a fixed target, and it will pass only the component we are receiving from the moving target. So now that fixed target signal, okay, that are nothing but a DC component, okay, and AC component means nothing but that is from a moving target, okay. So now this delay line canceller will just act as a filter. It eliminates the DC component of a fixed target and pass the AC component of the moving target, okay, and then that is to be applied to the display, so that, or that signal is to be given to the display here. Now what happened here, what is the role of this particular delay line here? So your signal will be divided into a two particular component, okay. So one, that what we can say, that a video to through the delay and direct video, okay. So that input is to be given to the subtractor there, okay, and then we will get the output, whatever the two channels we are giving input to the subtractor there, and that these particular two channels are subtracted, and the output of that subtractor is nothing but what, whatever the input we are providing, that is about a bipolar video, that will be the output here, okay. That is nothing but a, in the form of a unipolar, because we are converting that, here we are getting the bipolar video, okay, output is a bipolar here, but we are using a full subtractor, so that it will convert a video into a unipolar one, okay. So we are getting the unipolar, and this one is nothing but what, a simple example is to cancel the whatever the echo we are getting, that is from the stationary object, okay. So this delay line canceller is used to separate out the whatever the echoes we are receiving from the stationary object, okay. But what happened, sometimes if that repetition frequency, okay, echo signal frequency, okay, or you can say that the response we are getting from this delay line canceller, okay, even if that delay line canceller, that output we are getting, that frequency and the moving target frequency is same, okay. So that is nothing but what, where that component we are receiving at a receiver, that component has both the signal from what, echo from the radar, that stationary target, and echo from the moving target, okay. Sometimes what happens, whichever the echo we are receiving from the stationary object, the frequency is same, okay. So in that case we are getting the, what you can say, that output will be 0, and that happens when we have the a blind speed. So blind speed occur, where blind speed occurs when we have the fd is equal to what, twice of whatever the vr we have divided by a lambda, okay. So vr, okay, so this vr is nothing but what, whatever the velocity of your target there, or we can write in another way also, okay. Instead of that vr, we can write in another way, what will be the number of repetitions of the frequency occur, okay, at what particular period of time, by a ATP, okay. In that way also we can write, or we can say that TP is nothing but what, a pulse repetition time, or we can write in terms of a pulse repetition frequency. So at what particular pulse repetition frequency, FD, okay, this occurs. FD means what, nothing but a pulse repetition frequency. So generally what happens, the delay line canceller will eliminate a component from the clutter. Okay, it will eliminate the component from the clutter, and that component nothing but ADC component. But in addition to that, it will remove the component from the moving target, whose frequency, okay, whose Doppler frequency is same as the pulse repetition frequency. Okay, it is same as the pulse repetition frequency. Okay, so that is called as what, a blind speed here. So whatever the relative velocities we are getting from this MTR radar, okay, so that will provide you the, that will get, that will tell you what will be the blind speed there. Okay, so generally we can say that we can say that a zero, because from at this particular pulse repetition frequency we say that the relative velocity of the moving target will be a zero, because at the same times we are getting the frequency FD. Okay, that's why we are getting the a blind speed. So generally, if you see that this delay line canceller, it is just like rejecting the stationary clutter at a zero frequency. Okay, stationary clutter at a zero frequency. If the target, that their pulse repetition frequency is same, then your response will be a zero then. And this delay line canceller, it is operating only in a time domain, so that's why it is called as a time domain filter. Now if you see the response, okay, if you see the frequency response function of this particular delay line canceller, so that frequency response function with respect to particular frequency, so it will be what, we have the h of f. Okay, you can see that I'll just write that a h of f is equal to what, twice of sine phi f d dp. And we can say that from the single delay line canceller, the signal from the target at a given particular range, that will be given to the detector. So in that case, signal will be what, V1 k sine of twice pi f dt minus phi c. And this fd is nothing but what, a Doppler frequency, and this k is nothing but a constant here. Okay, that is nothing but for the given amplitude of a signal here, and phi 0 is nothing but a constant for the a phase there, and that phi 0, that is equal to the, in terms, we can write in terms of the range also. Okay. So or we can say that phi 0 is equal to 4 pi r 0. Okay, so that is nothing but what we can say, that 4 pi r0 by a lambda, that is about a phi. And that r0, we can say that it is nothing but a range here. Okay, this way we can say that it is about the range where we have the time equal to 0, and this we get the a signal now. Okay, that is about the response signal from the target we are getting, and then the signal from the previous radar transmission, which is similar to the whatever the delay, because we have the signal is about a delayed signal and a input signal. So in that case, we can find out, okay, that particular signal, because delay line cancel, we are providing the input directly, and another input is from the delay line cancel. Okay, so this is about your delay line. Okay, so we can say that the signal from this previous radar transmission, okay, so we can say that that is to be delayed by time tp. Okay, so that's why we have a two signal there, one is delayed signal and another is a direct signal. Okay, so we can say that v1 and v2. So if that signal is delayed by a pulse repetition interval, that is about a tp here, so in that case we are getting k. Your equation is about the same here. Only there is a change of what? Twice by fd. There will be about t minus tp. Okay, there is about a delay with respect to whatever the pulse repetition frequency. Now, if you solve it, this equation, after subtractor, what we are getting? V1 minus V2. Okay, so at a subtractor, we are getting a V1 minus V2. V is equal to what? V1 minus V2. That is about it. After subtraction, we are getting. And that will be equal to what? Twice of K sine of, if you solve it with respect to that, is sine A minus sine B. Okay, so that is nothing but a twice sine of A minus B by 2 into cos of A plus B by 2. Okay, so if you solve it using this equation, okay, from the sine A minus sine B, so we are getting twice K sine pi FD, that is about a pulse repetition frequency, and a cos of, okay, right here, a cos of twice pi FD T minus TP by 2, okay, minus pi 0. Okay, this one. This one is about a V. That is about the output. Output from the delay line canceller that we are getting, it consists of what? A sine as well as a cosine term. And that these to both the terms, if you see that they are related to your Doppler frequency shift MD. Okay, so that is about the MD. Only the change is what? Whatever the input we have. Now, if you consider that whatever the amplitude we are getting, that amplitude of a given particular signal, again it is depending upon the, you can say that we are that output is depending upon the what will be the Doppler frequency. Okay, so this way we are getting FD TP, FD fixed, TP is fixed, so we are getting directly this one is about the amplitude for a given particular signal, and then that will be depending upon the Doppler frequency shift. Okay, so this one is about the output. In the case of what will be the Doppler frequency shift and the pulse repetition frequency, this one TP here. Okay, so your output will be cancelled. Okay, video output will be cancelled when your Doppler frequency shift and that TP here. Okay, at what, if it is the same, then it will be cancelled. So what we can say that the amplitude of that particular cancel video, that will be depends upon the Doppler frequency shift as well as the what you can say that a pulse repetition frequency. So frequency response function of a single delay line canceller, we can say that we can write in the form of what? H of twice of sine FDTP, means it is depending upon the Doppler frequency shift as well as a pulse repetition frequency. Okay, so we are getting. So just like a single delay line canceller, it eliminates a fixed clutter. Fixed clutter, that is nothing but a from a stationary object. Okay, fixed clutter, but it has a zero Doppler frequency. Okay, it has a zero Doppler frequency. But again, sometimes if you consider that we are getting the echo from the clutter with the same frequency. Okay, echo from the clutter with the same frequency with a whatever the moving targets. If it is the same, so then delay line canceller will eliminate that particular signal. So that is nothing but a blind speed we can. So we can say that the delay line canceller from this, okay, so from this particular equation, we can say that the delay line canceller, what it will do, the frequency response function has a zero response when a moving target, okay, when what, the moving target has a same Doppler frequency, okay, at the given pulse repetition frequency. So in that case, h of f will be h0 there. Okay, so what we can say that is about a clutter one. Okay, so we can say that we just consider that if there will be a clutter spectrum, okay, at a zero frequency, Zero frequency means what? Because it is about a signal from the stationary object. Okay. So that's why that clutter frequency signal we are getting from the stationary object, it is depending upon that what will be the zero width of that particular h of f function, or we can say that frequency response of this particular delta function. Okay, that is about a delta. So what will be the width of that particular delta function? Okay, at a given particular frequency. So we can draw here amplitude of the frequency response function if supposed to be. I consider here this one is about a h of f here, and we are getting that fp. Here we are getting fp is equal to 1 by tp. Okay, this one is about twice fp. This one is about a thrice fp. Okay, likewise. So this one is about a output or magnitude response of h of f for a single delay line canceller with a pulse repetition frequency fp is equal to what? A 1 by tp. Okay, so that is about a response. And blind speed we say earlier that will be equal to what? Fd is equal to twice Vr by lambda. That is about a blind is equal to n by ATP. Okay, this one is about a blind is equal to what? N f. Okay, so that n is nothing but what? It will start from the 0, 1, 2. Okay, so likewise. Or we can say that the response of that particular delay line canceller h of f. Okay, this one h of f. Okay, and this magnitude sine of pi fdtp. This will be 0. Okay, so delay line canceller output will be 0. When it will be 0? When we have that sine of this particular term will be 0. And this 0 occurs when this pi fdtp is equal to 0. This will be this particular will be a 0. When this 0 will be occur at a 0 or plus or minus pi, plus or minus twice, plus or minus twice pi, plus or minus thrice pi. So means this particular function, okay, this pi FD if it will be 0, the h of f will be 0. Okay, so delay line canceller output will be a 0 when h of f sine of pi FDTP is equal to 0. When that sine of pi FDTP is 0, when we have a pi FDTP is equal to 0, okay, this particular term will be 0, then h of f will be 0. Or we can say that this whole term will be 0 when we have a plus pi, when we have plus or minus twice pi. Okay, so likewise, so we can say that minus thrice of plus or minus twice thrice pi. Okay, likewise. So we are getting that particular function will be 0, and from that we can calculate fd is equal to twice Vr by lambda. That is about a blind speed for the given particular a function. Now we say that here this will remove the delay line canceller will remove the DC component. It will eliminate the DC component of a stationary object. Okay, it also remove the, in addition to that, it will remove the component which has the same Doppler frequency at a given pulse repetition frequency of a signal. Okay, so that's what we can say that that is about a delay line cancel. That's why we have written that the FD is equal to what? We have written that FD is equal to twice PR by lambda, and thus FD is depending upon a pulse repetition frequency. Okay, so what will be the pulse repetition frequency? That is about FT is depending upon that a pulse repetition frequency. Or in another word, we can say that the response will be a 0. Okay, the delay line canceller response will be a 0. Okay, when we have the Doppler frequency shift FD is a multiple of a pulse repetition frequency. Okay, FD will be what? A multiple of a pulse repetition frequency. In that case, the response will be a 0. So means here we can say that a delay line canceller is to be used at a given single, okay, single what we can say the pulse repetition frequency. So even we can use the another way, okay, we can choose another way instead of a single pulse repetition frequency, we can use a multiple pulse repetition frequency to avoid the blind spot. Okay. So that is about another way to avoid the blind spot. And that radial velocities that will occur at the given particular blind speed, that can be obtained from the equation. We can say that we have a blind speed occur at the Vn, that is nothing but a blind speed when we have n lambda size of a t period, or you can say that n lambda fp by, and that n is equal to what? N is equal to what? 1, 2, 3, likewise. So this one is about a blind speed. Okay, so that is nothing but a blind. Just like we are replacing that VR with respect to Vn here. Okay, this is Vn. Why? There will be nth blind speed. Okay, so there will be a nth blind speed, and that nth blind speed occur at n is equal to 1, 2, 3. Okay, so first blind speed occur when we have that V1 n is equal to 1. Okay, and that this will be nothing but n is equal to 1. We will get that a first blind. Similarly, we can find out that a multiple blind speed at a multiple uh, value of the n there, and this occurs. Okay, this occurs when we have that blind speed occurs when we have that fd is equal to tp there. Now if you draw here at what particular pulse repetition frequency, okay, so we are getting the a blind speed. So if I draw here, okay, this is about a blind speed now, so we can say that this one is about a first blind speed. Okay, I supposed to be consider that at a given particular pulse repetition frequency. This one is about a pulse repetition frequency. Okay, this one. And at a given particular pulse repetition frequency, so we can get the multiple, okay, blind speed. So that multiple blind speed at a given particular range. So first blind speed for a given particular band, okay, this is nothing but this one is about a unambiguous range. Okay, and these are nothing but a different band. So I say that this one is about a VHF band. Okay, VHF band. Okay, say that L band. Okay, so S band. So likewise, if for the different band frequency, we are getting this particular pulse repetition frequency. This one is about 100 hertz. Then you can say that 1000 hertz. Okay, so you can say that 10,000 hertz. Okay, so likewise, you can say that a 100. Okay, 100,000. Like that. You can say that like that. So this way we are getting the blind speed. So this way we can represent a blind speed for this given particular pulse repetition frequency, and through that we can find out the unambiguity. And now this one is nothing but a limitations of the MTR radar. Okay, so this one is about the limitations of the MTR radar. So this means what? There will be a moving target of observed. Okay, but that moving target is to be cancelled with a undesired clutter at a zero frequency. Okay, so means target is there. Okay, target is present, but target is not able to display on the display device because of that a blind spot. Okay, so avoid this. Okay, so whatever this one is about the limitations of this MTR radar. So to avoid this, so we need to use, okay, so operate a radar. Okay, so we are getting a clutter. What we are getting a clutter because there will be the clutter, or we can say that a signal we are getting from the stationary object. Okay, frequency means we our echo signal. Okay, that is about AFT, and a clutter frequency is the same. So in that case, there will be a blind spot, we can say. Okay, or we can say that the signal we have the same pulse repetition frequency. So to avoid it, okay, so to reduce that limitations of that particular MTR radar regarding the effect of a blind spot. Okay, so to avoid it, so we can use operate that radar Okay, operate the radar at a long wavelength. Okay, operate radar at a long wavelength. Okay, operate radar at long wavelength means what? We can say that operate at a low frequency. Okay, operate device at a low frequency. But if we are operating the radar at a low frequency, okay, to avoid a blind speed, we need to operate a radar at a low frequency. But again, there are some limitations for the low frequency, because in a low frequencies there are a lot of applications are present. Okay, so generally we can say that our radar will operate at a what, a VHF band, UHF band. Okay, so likewise we can say, if supposed to be we are operating at a low frequency band, okay, low frequency band. For example, I am saying that it is to be operating at the VHF band. Okay, so in that particular VHF band, there are lot of applications are there. So if supposed to be we are using a uh, MTI radar, okay, to identify MTI radar for moving target identification there. Okay, this one. So in that case, what happened? So in the given particular band, there are a lot of applications there present. Okay, so this particular band, we can say that it is about a crowded band or a crowded frequency signal band. Okay, so in that case, we are getting a lot of signal from the different, I can say that different devices. Okay, in the given particular band. So in that case, again we are getting a clutter because same frequency signals we are getting. So then again there will be, but instead of that we are using a low frequency. Again another way we can use a narrow bandwidth. Okay, use a narrow bandwidth and a large beamwidth there. But what happen again if we are using a narrow bandwidth? Again there will be the limitations there to use this radar at a low frequency there, and then in this particular band of frequency there are a lot of applications we can say that FM applications there are, the TV applications are there, then we are not able to use this particular range of the frequency. Again we are using the same band, same frequency VHF frequency for the air surveillance. So this particular frequency has a low altitude coverage, and that low altitude coverage generally it is a poor one. So that's why attempting to use a low frequencies to avoid a blind speed, again there will be problem for the radar in a given particular specific band, because this one is about a crowded one. Another one, okay, another case is about we can use a high frequency signal. Okay, so instead of that low frequency, we can use a high frequency. If we are using a high frequency signal, then what happen? It will increases the a pulse repetition frequency. Okay, it will increases the a pulse repetition frequency. So means we can use either high frequency signal, or we can use operate the high pulse repetition frequency, or radar to be operated at a high pulse repetition frequency to avoid the a blind speed. But again, what happens here in the given particular case, the applications for this in the given particular frequencies are very small there. Okay, but if you calculate that, what will be the range of the radar there? Okay, to calculate the range of the radar, so we are getting using this high pulse repetition frequencies, there will be the maximum range calculations. Okay, is depending upon that a pulse repetition frequency. So what will be the maximum unambiguous range? Okay, so using a high frequency. So if we use a high frequency, the maximum unambiguous range for a given particular band is very small. Okay, so range. So it will affect the radar to be used at a given particular range. means it will use only for a small distance, okay, to identify the object within a particular radius. So that's why if we are using the high frequency, or if we are using high pulse repetition frequency to avoid the blind spot, there will be the issues of a range will occur. So means radar is to be operate within a particular range only, okay, or not in a long range application. So that is about a problem if we wanted to avoid the blind spot. Then another issue is about another case we can use instead of a single pulse repetition frequency, we have to use a multiple pulse repetition frequency. Instead of one, we can use, okay, more than one pulse. We can say that a multiple PRA. Multiple PRF means what? So we can avoid the blind spot. Okay. So there will be a two PRF or three PRF pulse repetition. So at a given pulse repetition frequency, even if supposed to be blind spot occur, so at different pulse repetition frequency, we are identifying the target. Okay. So if we are using a two, one or two or more pulse repetition frequency to avoid the a blind spot, so this using this multiple PRF, we can avoid the a blind spot because target can be identified using a different multiple frequency. So this one is about a use of a multiple PRF, okay, but that target will be identifying, okay, using a multiple PRF then. Okay, but this particular technique, they have some disadvantages because generally this particular technique is used in air surveillance radar to identifying what will be the air traffic, to control the air traffic, or to identify the any aeroplane in the given particular range there. But there will be the a drawback of the system if we are using a multiple PRF. So because of that multiple PRF waveform, we are getting the multiple time around echoes. Okay, multiple time around clutter echoes from the different component. Okay, so then again there will be the issues of what a maximum unambiguous range. There will be the issue we are getting the clutter from the region beyond that maximum unambiguous range, and that particular waveform or that particular multiple time around echoes we are getting from the clutter that cannot be cancelled. Okay, that is about the disadvantages of the multiple PRS. Another way to avoid the multiple another way to avoid the blind spot, that is about operate that with a different RF frequency, or we can say that more than one RF frequency. Okay, we can operate that radar operate with more than operate with more than one RF frequency. If we are operating the radar with a more RF frequency, so it can automatically unmask the blind spot. Okay, but the drawback of this particular system is what? It required a frequency changes because we are operating with a multiple frequencies. Okay, it requires a frequency change that will be possible within this particular given allocated band. Suppose I am saying that my this radar is to be operated in L band. So we need to use a radar with L band with a different frequencies there. Okay, that is about the limitations of the multiple frequency band. So it requires a larger band. Okay, so band allocated for a given particular user is a fixed. If we are using multiple frequencies there, so we require a larger band. So that will not be possible. Okay, so for a given particular specific band of a frequency. That is about the drawback of the system to reduce the a blind effect. Okay, blind spot. So We can choose another method. This one delay line canceller is used to remove the whatever the clutter there. Okay, so delay line canceller is used to avoid the clutter there. Then we can use another method is about a clutter attenuation. Okay, so generally we can say that we are using that a delay line canceller. Okay, that is used to attenuate the clutter for a given particular frequency or a particular spectrum there. Okay, so that is about a delay line canceller. But again, if we use, okay, this delay line canceller is to be used at a specific frequency spectrum. Okay, specific frequency, that the delay line canceller. This it will avoid, okay, that whatever the clutter is there, so it will remove that particular clutter, but it is not able to attenuate, okay, other clutters there. So that's why we are supposed to consider that what will be the another case is about a clutter attenuation. That clutter attenuation is used at a given particular frequency. Line delay line canceller only specific for a given particular spectrum. So instead of that, we will use a clutter attenuation at a different particular frequency. So generally, what happen here? We supposed to do the or we supposed to cancel the stationary clutter with a zero Doppler shift. Okay, stationary clutter with a zero Doppler shift. We have a zero Doppler shift. So that is about it. What you can say that what will be the zero Doppler shift. Cancel. Okay, but what happened? Some particular clutter spectrum, it has some particular finite width. Okay, so we are getting a clutter that will be removed at a given particular spectrum, but some particular clutters are there, they have the different widths. Okay, so in that case, if there will be the clutter we are getting from the moving target, okay, so generally we can say that we have a clutter from the stationary target. We can say that a clutter from the stationary target. But if supposed to be there will be a uh, there will be the you can say that internal motion of the clutter. Okay, so in that case, so it is difficult to remove that particular clutter there. So we can consider that to remove the clutter, so we use a specific frequency band or specific particular filter to remove the a clutter there. So generally we can say that in MTR radar we are using a stable oscillator. Okay, we are using a stable oscillator. Then we are using a coherent oscillator there. But there will be some at some particular point, if supposed to be there will be the some imperfection occur in the given particular device, that oscillators or signal processing system. So in that case, there will be the a clutter of, okay, and that particular clutter we need to remove. Okay, so what will be the clutter occur from the what can say that improper devices or instabilities occur in the oscillator. So that clutter is to be removed. So what will be that clutter information there? So clutter information occur from those devices. They have the Gaussian response. So we can find out here, or we can explain the clutter from the given devices. That will be what a W of F. That is about a clutter spectral density, and that will be represented with respect to a Gaussian function, exponential of minus f square by size of sigma c square. Okay, is equal to, you can rewrite again, W0 exponential of minus f square lambda square by 8 sigma v square. So this occurs when we have the f is greater than or equal to 0. Okay, this one will occur when we have the f is greater than or equal to 0 then. And this f0 is nothing but what? A peak value of a weak clutter. Okay, you can say that that is about a clutter. Okay, so you can say that this one is about a clutter we are getting, and that clutter for spectral density. Okay, that is about peak when we have a f is equal to 0. And sigma c is nothing but what? Sigma c is nothing but a this one sigma c here. Sigma c now. Okay, sigma c is nothing but what? A standard deviation of the clutter spectrum, and sigma v is nothing but a standard deviation of the clutter spectrum in meter per second. This one is the hertz, this one is the second. Okay, so we can find out here from this to what will be the frequency response. Okay, so what will be the frequency response of this finite width clutter spectrum? Okay, so I'll just draw here. This one is about frequency response of a delayed single line clutter there, about a clutter spectrum. Okay. So we will continue next lecture. Thank you all.